Alright, hey guys, it's Miss Summers with some notes today on Kepler's laws. So yesterday you should have taken some notes and done some practice with Kepler's laws. So today I just wanted to re-explain it, give you a couple more visuals to look at to really make sure that you're okay with this concept. Alright, so the first thing I'm going to show you is this little piece of paper that really, if you boil everything down, this is what Kepler's laws are all about, okay? The first law is about the shape of an orbit. The second law is about the speed of an orbit. And the third law is the time it takes for a planet to go around its orbit. All right, so I wanted to show you examples of all three of these things, okay? So the first one is the shape. So remember that according to Kepler's first law, planets orbit in ellipses. That means they go in ovals. So sometimes they're a little bit closer to the sun, and sometimes they're a little bit further away. And I want to show you how ellipses can change. You remember we talked about this word eccentricity? Eccentricity is basically how stretched out an oval is, or an ellipse is. All right? So I want to give you a diagram of this by drawing some ellipses. And to draw an ellipse, you actually don't have to be a really good artist. It's actually really easy. All you need is 2 push pins, some string, and a piece of paper. All right? So remember, in a planetary orbit, one of the foci, which is this yellow push pin right here, represents the sun, or the star that the planet goes around. We're going to say it's the sun. So I'm going to draw a little sunshine around this little guy. Okay? I'll color him in, because I want to. Okay? There's the sun. The sun's going to stay there in the center of this little solar system I'm about to draw. Okay? My next foci, there's nothing at the next foci. It's just empty space. So I'm going to just put it right here, really close to one another. This is line paper. Each of these little lines is about 0.8 millimeter or 0.8 centimeters apart. I'm just going to note that in a little chart that I have here. 0.8 centimeters. Okay. And now I take my string, or in this case it's like a little headphone wire that I found and cut up. And you're going to turn this into a triangle. You could do this at home if you wanted to, if you were so inclined. You would turn this into a triangle, which is going to do any second now. And you would draw your orbit. All right. Now I'm going to take this foci away, because remember, there's nothing there. And you might be saying, Miss Summers, that looks an awful lot like a circle. And you're right. This ellipse has a very low eccentricity. All right, so I'm going to measure this side to the sun and then this side to the sun to show you that it's not a circle. Okay, so from this point to the sun, this is approximately 9 centimeters. And this point to the sun is approximately, and I'm measuring to the center of the sun if you wanted to recreate this demonstration. This is 9.5 centimeters. So even though it looks really circular, this side's a little bit closer. It's a little bit closer at this side and a little bit further away at that side. Remember, this is called perihelion, around the sun. This is called aphelion, away from the sun. All right? So let me do another one. So, centimeters. I'm putting this down into a chart for my purposes. So that's why I'm writing stuff down. So now I'm going to try it again. But this time, I'm going to move the foci away. So the sun is still in the same spot. But this time, I'm going to move this. Let's move it. That's 0.8, 1.6. Let's move it here. So this would be 2.4 centimeters away between the foci. All right. I'm going to take my little string. This is the exact same thingy I just used. I'm going to put it around there. I'm going to make a triangle, and I'm going to try to make this. Whee! All right, there we go. And you might be saying, oh, it looks smaller. It's not necessarily that it's smaller. It's just one side got closer, all right? So I'm going to do the same thing. I'm going to measure perihelion to the sun here. In this case, perihelion, right there, I'm going to put it down here so you can see it. That's about 7.7 centimeters. And over here at aphelion, for this orange line, this is about 10.3 centimeters. And I'm going to write that down on my chart, 7.7 centimeters, 10.3. So the difference between aphelion and perihelion has increased. This is becoming more of an oval and less of a circle. All right, let's do one more just for funsies, just to really make sure that I am not crazy. And let's take this one. Let's see, 1, 2, 3, 4, 6 times 0.8. Let's see, 0.4. Starlight, stop it. That's my cat, everybody. Let's see, 2.4. That would be 3, 3.6, 4.2. Let's do here. So the foci are 4.9 centimeters away from each other. All right, take my little thingy, drawing a circle, which is not a circle, it's an ellipse. I would yell at you if you said this was a circle, so I will yell at myself. Miss Summers, that's not a circle. All right, and here we go. Whee! Whee! All right. So again, I don't want you to focus on the size. I want you to focus on the shape. All right? So again, I take this foci away because there's nothing there. Look at how close this side is to the sun. Key right here. This is perihelion. Super, super close. Aphelion's way the heck over here. Let's measure them just to prove my point. Because I love being right. Here, aphelion is 5.1 centimeters away. And here, on the other side, this is perihelion, not aphelion. I misspoke. And over here at aphelion, it is about 7 centimeters away. All right. So as these distances between the foci increase, the difference between the distance from perihelion and distance at aphelion get bigger and bigger. All right? So keep that in mind. All right? So the first law is basically saying a planet is not always the same distance from the sun. Okay? Sometimes we are closer and sometimes we're a lot further away. It just depends on the eccentricity. If you have a really high eccentricity, those distances can vary greatly. All right? So let's go back to our second law. The second law is about the speed of a planet. So I'm actually going to jump back to my computer screen here for a second. I'm going to go to my screen on Google Chrome, and I want to show you this little visual. Okay, just take a look at it as it goes. This is really boring. Okay, so we have this planet. Remember, the second law states that you sweep out in equal areas in equal time intervals. So note these triangles. This orange triangle has an area of 4,450. So does this yellow one. So does this red one. So does the next one. All right, and you'll note this is showing the orbit of Venus, which has a very low eccentricity. It's almost zero. It's almost a perfect circle. But I want to show you a different one. Let's look at Mars. Okay? So Mars, again, the areas are sweeping out. They're equal areas. Each of these triangles are the same. But look how it gets a lot closer here. And you see these triangles here are a little bit wider. And this one, now it's getting further away. It's almost at aphelion. It's moving a little bit slower. The easiest one to see this, if we take the eccentricity of a comet. All right, comets have very high eccentricities. They're very, very oblique. So they get really, really far away at aphelion and really, really close at perihelion. Note what happens at perihelion. It slingshots around. It goes a lot faster. All right, so imagine like a little slingshot. The closer you get to the sun, it picks up your speed. As you get farther away, it slows down. You're always going to be moving fastest at perihelion and slowest at aphelion. Okay? And let's jump back here. So we've talked about this shape. It's an ellipse. If the foci of the ellipse are far apart, the ellipse becomes more eccentric. This speed changes based on where you are on that ellipse. If you're close to the sun, you're going faster. And if you're far away, you're going slower. The last one is time, okay? And before I even show you planets, you can think of Kepler's third law like a racetrack. Okay, so I have my little racetrack I made. I'm so proud of it. And I have these two cars that I stole from my child's toy box, okay? I'm going to put them right here. They're going to start right here. It's a fair race, right? No, it's not. Of course it's not a fair race. All right? If I move these cars at the same speed, whee, whee, you're going to notice that this car, the orange car, the one that's closer to the middle, it's already finished one lap before this one's even made it a quarter of the way around. This ring right here is a greater distance than this one here. And that's the beauty of Kepler's third law. He says the same thing about planets. He says, if this is the sun, now I'm going to do a little magic here, excuse me. Here's the sun, okay, in the center of our solar system. If you're Mercury, which is right there, it's not going to take you very long to go around. It takes you a very short amount of time. If you're a little further out, like Venus, it's going to take you a little bit longer, but not much longer. And then if you get out here to like where Saturn is, this is Saturn, everybody. It's beautiful. It's Saturn, I promise. All right, it takes you an even longer time. And then if you're way the heck out here like Pluto, poor Pluto, it's going to take you a really long time. Okay? That's essentially what it's saying. And we can see this. There's a way to think about this. Your age on other worlds. So I went ahead and filled this in as if my birthday were yesterday, August 22nd. You're doing this next week, so this is a week. Just pretend it's the date. Just pretend. Okay, somebody who just turned 17 years on Earth, okay? They've been around the sun 17 times. If you are on a planet that was closer, you would have gone around more times. It doesn't take as long for a year to occur. So on Mercury, a year lasts about 88 Earth days. So if your birthday is in August, well, the next time Mercury goes around the sun, it's only going to be October on Earth. All right? But if you're on a Jovian planet, which are the gas giants, like Jupiter or Saturn or Uranus or Neptune or even Pluto, even though it's not a planet, it would take a really, really, really long time. Look, on Saturn and Uranus and Neptune and Pluto, you wouldn't have even turned one yet. You would still be waiting on that first trip around the sun. It would take that long. Fun fact, Pluto was discovered in when was Pluto discovered? 1930, that's what I thought. Okay, Pluto was founded in 1930, so it's been 90 years since Pluto has been discovered. It hasn't even gone around the sun one time since it's been discovered. It's only made it about halfway through its orbit because it's so far away from the sun. Okay, so I hope these were helpful. you have a lab assignment to do. If you have any questions, you can email me or see me on Monday. I will be available by email if you want to chit-chat about these topics. I would be happy to answer any questions. And if not, I will see you the next time I see you.